So hello and welcome to today's VELOVirtual webinar. Today we're going to be talking about a very cool part, literally and figuratively, a part that would not be feasible without additive manufacturing, or more specifically, without Velo3D support-free processing. Let me introduce our speakers. Joining me today, we have three fantastic speakers. Enrique Enriquez is the president of KW Micropower. He is a former Rolls-Royce aerospace engineer. And for the past 20 years, he's been developing microturbines for shaft power and turbojets. His teams have been everywhere. They've developed several microturbines for the US Army, DARPA, Spayware, Northrop Grumman, and Boeing. So some massive major companies here. He presently leads KW Micropower in developing a line of advanced microturbines, which we're going to get into today. I won't reveal too much. Pretty amazing stuff he's doing. Also joining us today from nTopology is Dr. Ryan O'Hara. He's the technical director for aerospace and defense at nTopology. He joined nTopology in April 2019 after serving 20 years in the military with the US Air Force. Thank you for your service as a developmental engineer. His technical focus is on application of mechanical structures and structural dynamics to aerospace systems. Some of the areas of interest include turbine engines, obviously, laminate composites, metamaterials, and additive manufacturing, of course. Joining us from Velo3D is Gene Miller. He's an applications engineer. He joined Velo in 2016, one of the original guys, as a process engineer working on what makes Velo3D so famous, the support-free metal AM processes. And prior to joining Velo3D, he held various positions in foundry and process engineering, and he holds a BS in mechanical engineering from the Colorado State University. So now I'm going to turn it over to our speakers.
Hi, everyone. We at KW Micropower are aiming to build the smallest, most powerful and lightest generators for aviation and ground power. Obviously, the way we intend to do this includes a lot of 3D printing. And that is pretty much our goal. We intend on doing this, obviously, by combining the most powerful software package available with the best 3D printing capabilities that we have found. So this is my team that is helping me to make our generators as lightest, smallest, and most powerful as they can be. Okay, this is our 30 kilowatt generator that we're introducing soon, hopefully this year, by mid-year. In it, there is quite a number of components that have been 3D printed, and we'll get into that in a little bit. And our generator, this one here, produces 30 kilowatts. Its dimensions are about 15 inches in diameter by 30 inches long. It spins at 90,000 RPMs. It runs on diesel, Jet A, JP8, natural gas, and biofuels. So the part that we're going to be covering in this case study is the one that you see here at the front, and that is the generator case. Okay, 3 years ago, I had a big problem. I had a difficult part that nobody could make. And this was one of the key parts in my engine. So with that problem, I went to IMTS looking for a solution, looking for somebody that would save me. Because if not, I was just going to have to redesign the whole thing. So I happened to run into an old colleague of mine, aviation consultant, very intelligent fellow that knows a lot about manufacturing high-end components. And I told him my problem. And he said, Enrique, if you're going to solve that problem, you got to go see Velo. They are the most advanced, most sophisticated 3D printing systems that I know of. I had not heard of Velo up until that point. So soon after, I headed on to Velo, and there I met Benny Bueller, the company founder. So I told Benny about my problem, and he said, let me get your information. We'll get someone to get in touch with you. Soon after, Zach Murphy, I think at the time he was the VP of partnerships for Velo. He contacted me. I told him about my problem, and I shared my information. And he says, let me take a look at it. I'll contact you soon. The short of it is that about a month later, not only have they come up with a solution for the part, they had knocked off 37% of the weight. And here you see the part. So, I mean, that just saved me. And we continue on our journey. And definitely at that point, I had become a big fan of Velo. So now that we have identified, the manufacturer for us, we also need and want to work with the best software package that can make me maximize each component. And for the next trick that we did with Velo, what you see here is an igniter system for our engine that previously was made out of 3 very tight tolerance Hastelloy components. So we were able to combine the 3 parts into one, and at the same time reduce the cost and reduce the weight of the component. So that was project number 2 that we did with the 3D printing. Project number 3 is the one you're going to hear about today, and this is the case for our generator. So from our billet configuration, when we started thinking of, well, now we want to knock off all the weight that we can out of this part, we started thinking, what else can we do? What else is there anything else can we gain? Are we leaving anything on the table? And one of the great things that we could do was to cool it. If we could find a way of running fuel through that part, we would have a couple of gains. Not only will we bring the temperature of the case down, which in turn helps the generator, but we will put all that energy into the fuel, which downstream will help my combustion and make it more efficient. So that is the premises of what we intended to do: knock off weight and run fuel through it and cool the case and put all that energy into the fuel. And in order to do that, Zach told me, look, we're going to need to work with nTopology. And I said, who's nTopology? He says, well, nTopology is the most powerful software package that we know of out there that can maximize your design. So he put me in touch with Ryan O'Hara, who has been just brilliant in his work. And without much further ado, I would like for Ryan and Gene to take over and tell you what it is that they did with this part.
Hey everyone, I'm Ryan O'Hara. Happy to be here. Glad you could all attend. Hopefully you guys will get some good education or out of this. We'll see how things go. Let's see. So just real quick background on, hey, what's nTopology, right? And so nTopology, we were founded in 2017, or actually in 2015, and released our first product in 2017. And that product was focused on periodic structures. And then in 2019, we released our latest product called nTopology Platform. And the idea is that's a computational modeling software for design, simulation, and then advanced manufacturing. And so we'll touch on each one of those areas today. And the key differentiator for our technology is that in most traditional CAD or CAE tools, you're using boundary representation data. So that's like a SolidWorks or Dassault or Siemens. And the idea is that you have a patchwork or a quilt of needed to represent geometry, right? And then our fundamental difference in our technology is we're representing geometry as implicit math equations. And the idea is that instead of storing hundreds or thousands or even millions of these surfaces to represent geometry, we just have one equation, and we discretize that equation when we need to, whether that's for visualization or simulation or manufacturing, right? And then when we think about math and geometry, we can actually take fields, right? And we deal with fields in all our lives, specifically like fluid fields or stress fields when I think of a FEA or simulation background. And those are kind of all represented here below in this image. But we can take those and we can actually use those as modifiers. And we're going to talk about how we did that for a shelling example here. And then fundamentally, we provide a method to allow people or engineers or designers to like reproduce workflows, right? So in some ways, we've heard our software referred to as a visual programming software. We're not going to dig too much into that, but I will refer you to our website or YouTube if you want to like go down that rabbit hole to learn more. And I'd be happy to go with you too. So maybe we'll do that a little bit here now. Spoiler alert, Enrique came to us with a problem. He had a generator housing. It was basically a thick piece of material designed for traditional manufacturing, right? Probably a combination of multi-axis machining with some wire EDM, basically taking a big chunk of metal and then removing material to do that. And fortunately, when Enrique came to us, oftentimes we encounter designs where some sort of engineer, and usually a really smart engineer, has taken their design and kind of optimized it for their manufacturing process. And then they often come to us and saying, hey, I want to take this to the next level. And we often say to them, hey, maybe you actually did a really good job of designing for your process. Maybe there's not as much help that we can provide to you. In this case, Enrique came to us a little bit earlier on in the design process, right? And we still had some flexibility and ways to improve this part. And it was real simple. Enrique had a heat problem, right? I have a big piece of metal. I'm only cooling it with air, but I have plenty of room to add some cooling. And I said, hey, I got a solution for you, Enrique, and it's super simple. And it's basically, we're going to variably shell this part. We're going to shell this part and we're going to fill it with a big cooling volume, right? And then in this discussion, early discussion, Enrique expressed that, he has fuel available, right? And fuel is often used in aircraft instead of just being a parasitic device or source of energy, right? Often it's pumped throughout the aircraft to cool things down, right? And I asked if we could do the same thing in this scenario, and he said, sure, right? And so this is kind of the concept we came up with. We basically have a generator housing, and then inside that, we're just going to fill this with a big volume, and we're going to pump that fuel around. But in addition to adding this cooling volume, we're also reducing weight, right? So we took about 40% of weight away, right? And we replaced that with this cooling fluid. And then we'll kind of get into how we did that and some of the things we did in our software to gain confidence in the design. And I mentioned before, this is kind of a home run for our software. So in traditional CAD tools, oftentimes when you need to shell a part, it can be quite difficult depending on the complexity. And so when Enrique gave us this original design, I actually tried in SolidWorks in this scenario to actually shell the part. And I instantly got an error saying that there was the quilt work of boundary surfaces wasn't going to allow me to perform that operation. However, in our software, it's easy peasy. It's about a 1 to 2 minute setup and operation. And then the idea here is that we could actually take a field, and I'm showing an example here where we took a topology optimized part that is normally solid. We shelled it, but in this scenario, we actually used a stress field to variably shell this part. And then for Enrique's design, we actually, I basically have the shell being thicker at the top and bottom because it's the critical interfaces for mounting. And we preserved the geometry, and we kept it relatively thin in the middle. So effectively creating a monocoque structure. So with that said, kind of get to the goodies. The idea here is that we added almost 2 liters of fluid for cooling volume. In this case, it was going to be jet fuel. And then what we did is we were actually able to, in our software, run or take the geometry, the shelling operation that we did, and working with one of my colleagues, we ran an ANSYS Fluent simulation. We'll talk about that. But we basically were able to calculate the fuel heat transfer coefficient so that I can actually do a simpler model in the design phase of this quite quickly. And I can do that all inside of our software. Fundamentally though, what we did is we took the external temperature and we took it from being about 190 C or 380 degrees Fahrenheit. So basically really hot, right? Like creating an oven there. And then we actually were able with the fuel to cool it down, cool the exterior of the case down to about standard temperature and pressure, right? So which the fuel is at in its storage tank. And fundamentally, we're also heating the fuel, right? And I think Enrique can talk to this a little bit more in detail later. But the idea is that we can take that fuel by transferring that energy, we're conserving that energy, and then we're basically preheating the fuel so that it's going to combust more efficiently. So kind of a win all around. And then real simply is we took the internal geometry, and this is the ANSYS Fluent heat transfer simulation that we did, but we're able to calculate this heat transfer at the walls, and I was able to apply that as a boundary condition in our software. And just real simple, in this scenario, we took the part that has been shelled, we generate an FEA mesh inside of nTop platform, and then that's a surface mesh, and then ultimately this FEA mesh. And then in addition to modeling the generator, so in this case, at a 30 kilowatt generator, Enrique has said in the past he's able to achieve like about 95% efficiency. We assumed that about 5% of that was going to be waste heat. So about 1,500 watts we're applying as a source of heat inside of this. And that's per based on that surface area. And we're actually modeling the heat transfer here now in this in our thermal solver. And then we're also modeling forced convection. So Enrique is using this generator to actually pass air to feed the turbine itself through to provide additional cooling, right? And then ultimately get some free convection. And when we set this up in our FEA problem, we end up with a thermal simulation. And the idea here is that, we're able to visualize, the heat load path in this scenario, right? So relatively simple. And the idea here is in our software, we have a series of blocks on the far left that represent, the different forms of the geometry that we're bringing in and transferring to implicits and ultimately into an FEA model. And then just a quick visual of what's going on inside of this part to get to where we were. So I think with that said, again, just want to reiterate, this is a huge, not only are we, in aerospace, right? If we basically, within a series of a few operations, we're dropping our mass by 40%, right? And I'm providing an exterior cooling or temperature drop down to, near static temperature and pressure. As in preparation for this, I think all of us, Gene and Enrique and I, we all talked about this. Is like, this is a real simple win. It's like, I made your part stupid light and I made it really cool. Like wash my hands, done, high five everybody and win, right? So it wasn't in this sense a terrible engineering problem, but it's really the culmination of bringing a need, right? Some advanced design, being able to do a relatively simple operation, you would think, called shelling, and then actually applying that here to this part, and then fundamentally manufacturing it. And with that said, I'm going to turn things over to Gene.
Thanks, Ryan. Hi, everybody. I'm Gene Miller, and here to talk about the fun part of this whole project is actually manufacturing it without the need for any type of compromise. The real big win here was to take all that work that Enrique did and all that work that Ryan did and say, yeah, sure, let's print it. We don't have to go back to the drawing board. We don't have to compromise. We don't have to make any changes. So with that said, we're going to talk about, a real high level. This is what a laser powder bed fusion system does. And in a conventional sense, you'll have a piston inside a cylinder that moves down a designated length of distance, and that's your layer thickness. In our case, it's about 50. It is 50 microns. And then in the middle here, you see what we call the recoder. And on a conventional metal AM system, the recoder, I like to call it a dump and smear method. It kind of just plows a bit of powder over the top of the part and leaves a thin thickness of powder to be melted selectively by the laser. And every layer, happens iteratively, and eventually it builds up to complete your printed part at the end of the day, and then all the unfused powder is removed and recycled. But that is essentially on a high level how a typical laser powder bed fusion system works. So in a conventional metal AM system, these challenging features that we have to overcome are supported. Supports are really, they're not there to prevent the part from collapsing or anything. They're actually there to keep things anchored down and constrained so that the internal stresses that are developed during printing don't cause deleterious warping and movement of the parts. If you look at the desired outcome on the left here, this is essentially what we would want to print, but without any support material, these overhangs tend to warp upward and can tear themselves apart and cause recoding to be impossible. So what the conventional solution is to add supports to these low overhangs. And that's what we're showing here in the red. These are support material that's added to the part. And that's fine if you can access that material and remove it after you're done printing. And in this case, we have some really isolated volumes which are inaccessible after printing, and you just can't get in there to remove any of the support. So we can't put it there, but the good news is we don't have to. So here's a kind of a comparison between a conventional DMLS printer supporting scheme versus a Velo3D Sapphire. Everything on the left under 45 degrees has added support material added to it. And you know, some of the areas are accessible in the center of this part, but the enclosed volumes that are inaccessible where there would be support on a conventional system just don't make sense. You can't get to this after printing, so it's, you know, you're kind of printing garbage. The Velo3D Sapphire printer has no need to put support on these internal volumes. So at the end of the build, all you have to do is just remove the powder from these channels, and they're open and free flowing, and you know, no need to add any support material. So how do we do this? You know, it's kind of biting off smaller pieces and applying specific laser parameters to specific geometries in order to get a desired outcome without the need of adding support. We have our preprint software package that Velo3D designed. It's a preprint kind of a 3D space where the user can import a CAD part. They can orient and add support, and then click prepare for build. Now Flow automatically recognizes all the geometries in this part and applies specific laser parameters to ensure successful printing without the need for added support material. In this case, for this part, we have certain geometries like closures. There are tall vertical walls. There are some low overhanging features that go below 45 degrees or even near 0 degrees. And then there's also some bulk core where, you know, you really want a specific laser parameter to put down as much material as quickly as possible to really enhance your print time. This discretization of laser parameters really helps us achieve unprintable geometries in other senses and really still be competitive as far as a throughput sense. So on a high level, here's how the support free is enabled by the non-contact recoder. We have a powder dispenser that kind of snows down gently a thick layer of powder over the substrate of the powder bed. Now, behind that is a normalizing blade that then flattens and normalizes that surface after it is dispensed. And then behind that, that's where the magic happens. That's our proprietary powder removal tool that comes in behind the normalizing blade and removes all but 50 microns of powder. So the net is the same. We still have a 50 micron thick powder bed, each layer, but we never actually come in contact with the part. We don't have to worry about movement or interference with the recoder. So the Velo3D platform, we call it a full stack solution. There's 3 tiers of our product. First is Flow, I mentioned that earlier, where the engineer takes their CAD or their design intent, brings it into a 3D space. They can orient, add support material if necessary, process overrides, and then actually prepare the print file. And the print file is what's taken over to the Sapphire printer, and that's where the real printing happens. That's where we recoat, we selectively melt, and print the part. Now, all throughout that printing process, there are literally thousands of sensors gathering data on this machine, and we needed a way to compile it in a really concise, graphical, friendly to the user interface. And that's where Assure comes in. Assure is our quality validation software. It's designed for real-time monitoring of the builds as they're being printed on the Sapphire machine. And also, after the build, we produce a very concise, clear build report to validate the quality of the part. So going through this build in particular, it starts off pretty typical. There's some bulk material here, and where this little clip ends is at the beginning of the cavity as designed by nTopology. There's nothing really challenging about this yet, but this is where this part starts to get interesting. This is where we've got these open cavities as designed by nTopology. So moving upward from there, The walls are pretty thin. They start to get pretty tall, especially these internal bosses and tubes can be subject to recoder interference. As they get very tall, they get flimsy, and any lateral force could move that thin structure around. And on a conventional metal AM printer, that might be problematic. It's just something that we don't have to worry about because of that non-contact recoder. Then lastly, these internal cavities close out without any added support material. Again, they get a specific laser parameter so that we don't have any real degradation of surface roughness at that closeout, as well as no need for added support material that in this case would be impossible to remove. And here's the printed part. This is right out of the printer, ready for final machining. This part was about 9 inches round by 9 inches tall. It's printed in aluminum F357. The overall print took just under 3 days. It was about close to 5,000 layers. And, there's this line that you see here is an artifact of the internal closeouts and internal passages kind of causing a difference in thermal history, but it's all cosmetic. We were really pleased with how this came out. All the internal passages are free flowing and able to do exactly as intended by Enrique and Ryan. And now I'll hand it back to Enrique to kind of summarize what we talked about here today.
Basically, the message here is design without limitations. What I call it is a great opportunity for today's engineers to really be able to go back and look at everything and see, can I do it differently? Not just knock off weight off of it, but is there anything else that I can gain? Can I put a probe here? Can I put a sensor there? What else can I gain? And when you start looking at every part, then you see gains all over the place. Like, for example, we're going back to the drawing board. There's more work to be done with nTopology and Velo for me, as you can imagine. So I'm a glutton. I want to completely devour this opportunity. So for the rest of you engineers out there, it's what I call a renaissance of engineering. You just go out there and look at a part differently. Now you're not limited by the conventional machining methods. And that's my message.
All right, thank you, everyone. Great presentations today. We do have a lot of questions coming in, and so I'm just going to kind of work our way through it one at a time. So for the first one, Gene, what's our most popular question?
How does the non-contact recoder work? I thought I explained this.
No, the number one. The number one.
Oh, how do you enable support free?
Yeah, how does Velo 3D print parts without support? So that's actually was the first question asked.
Well, I hope I touched on that briefly in this presentation, and there are other processes specifically that we apply to like lattices and thin walls, and there's a whole pedigree of laser parameters that we have ready to assign to your specific geometries, whatever it may be. We've developed them out of necessity, out of parts that we have seen over the years and challenges that we've overcome by developing internally these laser parameters and processes that we know work. And there's always new challenges, sure, but our baseline parameter set as flow runs through it does a great job of recognizing these geometries, saying, that's a low overhang, I need to apply a low overhang process to it, or whatever it may be, and creating a successful print at the end of the day.
A question kind of related to that is, does it integrate AI?
So, I mean, I guess in a sense, flow is intuitive enough to recognize these geometries, in some sense, yes, but it's not like, it's not Cyberdyne Systems or anything. It's not anything out of Terminator, but it's definitely an intuitive, useful software that is very user friendly in the sense that you don't have to be cognizant over every type of feature. Flow takes that out of your hands, and it's very generalized.
You mentioned some of the cavities are inaccessible. There's a question: how do you clean those cavities?
So we used a lot of vibration, a lot of shaking, a lot of diligence. You know, and you can use some compressed air on it. Aluminum doesn't really like to have compressed air put to it, and we try to avoid that. But you know, with a lot of tipping and shaking and tapping, the powder just comes out. It's all, you know, it moves like a liquid almost.
There was a question about seeing videos of the print in action. I can kind of answer that. If you go to the Velo3D YouTube channel, you can see a number of prints in action. I don't think we captured any of this specific part, but you'll get a very good idea of what it looks like if you want to see that in action. Enrique, a couple for you regarding the application. There's a question, what's the timeline look like for you to bring this into commercial production?
We're hoping this year.
Awesome, so we'll see it pretty soon. And there's a question, since the fuel is now hotter before combustion, were there other changes that you needed to make, for example, injection nozzles?
We have a proprietary system that addresses that. Yes, correct.
Okay. Yeah, I don't want to get into the secret sauce too much, right?
Yep.
And you mentioned you did ground applications as well. And so there's a question, do you see, you know, obviously weight savings might not be as important, but you've got the thermal cycle benefit. Do you see that all kind of justifying a change in the manufacturing process?
Well,
even for ground.
Yeah, I think it's going to be more customer driven. It'll be more of what is it? You can kind of put together your engine for your application. That's the way we're envisioning this. So you'll be able to mix match components according to what you're trying to get.
Okay.
Does that sounds like an answer?
Yeah, I think so. So a little bit of customization, market of one type of outreach.
Yeah, for some people, you know, that it's not that important for them to, you know, for the unit to be hot. They don't necessarily may care for have the most amount of efficiency out of the engine, but they just want a product that is a lot less expensive.
Okay. Gene, a couple questions regarding powder handling. Question regarding, is the powder recycled or is it reused?
Yes. So to a certain extent, you know, we monitor carefully the chemical composition of the powder, and there is a life cycle, especially with aluminum, that we found that, you know, there is a period of time where it does go out of spec. So we carefully monitor that, and we do change the powder out. With less reactive powders like Inconel or Hastelloy, we find that the life of the chemical composition being within the spec is much longer. Aluminum's a little bit more sensitive to that, and we're going through, you know, kind of the pain points of doing our diligence, cleaning out the powder and printing virgin powder. But throughout one single build, yes, the powder is laid down and recycled through a powder conveyance system and then redistributed on the powder bed. And that is done for, you know, however many builds until we need to essentially clean out the system and replace with virgin powder.
And regarding the size of the build chamber, what's the maximum size that a printer can handle in terms of parts?
So we have currently our first generation of Sapphire is 315 millimeters round build plate by 400 millimeters tall of build volume. That doesn't include the build plate. We also now are just releasing our 1 meter Z tall system, which is the same diameter, 315 millimeters by 1 meter tall of build opportunity. Later in this year and early next year, we will have Sapphire XC, which is a 600 millimeter diameter build plate by 550 millimeters tall. And we look to expand that even in the future, much longer term.
Excellent. Regarding print capability, what is the minimum resolution that the machine can print? Like how thin can your walls be, that type of thing?
Well, you know, that's a pretty tough question to generalize. It depends on the geometry. If you're printing a heat exchanger with very, very thin walls, I mean, we can print down to, you know, below 200 microns of a thin wall. However, you run into challenges when complex geometries start to merge and join together, and it's a potential for leak points. So you have to take those considerations as far as minimum thickness into consideration when you know, you have a part that needs to be leak tight. So yes, we have a very small minimum feature size that we can resolve, but is it really worth it in the actual geometry? So we'd have to look at the part and make a judgment call based on your specific needs.
Okay. So there are a couple questions here, Enrique. Well, maybe for everybody. Somebody's interested in getting some educational opportunities out, and there's are there any samples or rejected units that are available for educational purposes? If you have questions like that, or you want to repurpose today's presentation, please get in touch with me, marketing@velo3d.com, and I'll be able to answer that. So, we definitely look at outreach and education, take it seriously. So we'll take that offline, but I did see a number of those in there. So I do want to get back to you and get you the contact information. Let's see. Yes, the presentation will be available for download as well. It'll be a video that you'll get a direct link to. Okay, so regarding the part, what's the outer diameter of the part? Did you mention that earlier?
Yeah, the OD is like 9.17 inches in diameter.
Okay. And Ryan, I know I'm coming to you here. Regarding the design of the component, there's a question. The cooling jacket seems to have no internal fluid directing features adjacent to the ports so as to ensure uniform cooling. Was this considered unnecessary? Or would you want to comment on that and how that affected the design?
Yeah, I think in this scenario too, and we can go back, or if you needed to, we ran a fluid analysis on this, right, to visualize that the fluid flow, and we were happy enough with the uniformity based off of that, rather than adding any additional channels or serpentine passages. I think in this scenario, a key thing was also, I saw a question about internal surfaces, right? So this design would be easily extrude honed. So that's like like a putty with metal particles inside, and it's pushed through hydraulically to smooth passages. So we kind of wanted to balance all of those things in this scenario. So.
Okay. Gene, this is about removing powder. What's a minimum, I guess, aperture size that you would need if you needed to extract powder from the system?
Well, it's always beneficial to have an inlet and an outlet. So, to test, you can get some compressed air in to feel compressed air out. You have flowability. I mean, I've done something. It was a very, very short hole, but it was 500 microns, and it was just a straight tube. I would say anything below that, you're running a risk of capturing powder and not getting it out. But again, it's going to depend on the geometry. I mean, if it's something very, very complex with a blind hole rather than an inlet and an outlet, it could be much more challenging to get powder out of a smaller hole. So, it's generally is tough to answer and say you'll be fine in every sense. But, I can resolve a 500 micron hole and have flowability through it and get powder out of it. But that being said, there's caveats to any more complex geometry.
So your non-contact recorder question did come in. Is there anything else that you wanted to talk about with regard to the non-contact recorder? I know you shared a lot in the slide.
Yeah, it's the most unique thing that we have. Well, I mean, it's not the most unique thing we have. It's what our company was initially built on. And there's a lot of things that we're not really sharing globally or that publicly about it, particularly the proprietary powder removal step at the end. The sprinkling of the powder dispense is, hey, we dispense more powder than we would laze on. Then the normalizing blade comes and flattens everything out, but that's still, about a millimeter above the part. And from that point, what we remove by IP is, what we can't share globally here today. But I can say that it is repeatable. It's dependable. We have a structured light scanner that actually maps the surface of every layer of the powder bed. So we can quantify that we're getting a consistent layer thickness of 50 microns. We aren't seeing surface morphology anomalies. And even if we are, it's a great tool to help troubleshooting any issues that we might see. So that structured light scanner we call the height mapper, and it is hugely beneficial in qualifying our powder bed so that we know that we're going to get a good print at the end of the build.
Thank you. Well, you mentioned 50 microns, so I'll get into this. Is it possible to print with different layer thicknesses?
Sure. I know a lot of other companies or laser powder bed fusion systems use different layer thicknesses. It's something that you would design a process for. We have chosen 50 microns and designed our process on 50 microns, and that's what we use across the board. For higher feature resolution, we've experimented with different layer sizes or layer thicknesses, but it's not something that we roll into the best known method or the standard process that we roll out.
Okay, let me see here. Oh, is the material fully dense when it comes out of the printer, or is there porosity?
Well, so we have a porosity spec. We spec 99.9% dense material. That being said, there is some porosity in the part, but it is 99.9% dense. It's not laser powder bed, or it's not laser sintering. You don't need a fusion process. You don't need to put it in the oven to get fully dense material. It's fully dense when it comes out of the printer. We consider that to be better than a casting spec where you could have a lot larger sources of porosity depending on the geometry that you're casting. But yeah, it's fully dense. It doesn't need to be post-processed. If there is an application like an aerospace application that requires a HIP or a hot isostatic press process, that's an option. But that would depend on your specific application.
Okay. You mentioned before support free. Are there scenarios where Velo would use supports, and what would those be?
Oh yeah, absolutely. I mean, if we say support free, it doesn't mean this is the end of supports. It doesn't mean there's no such thing as adding material to ensure printability. I mean, big, large, massive parts have a lot of internal stress and like to warp upward, and that needs to be constrained. There are some opportunities where we can avoid it. There's a lot of opportunities where we can avoid it, but to print a part safely, especially a large, bulky part, you still need to add support material and constrain it to the powder bed. And you can see that in this print. There's a blending fillet at the base of the part that attaches it to the build plate. That's all support material that's intended to be machined away.
Okay. So there's one here, Enrique, I'm not sure if you want to share this or not, but what is the rough maximum overall power efficiency for the MGT you think you could reach using a full AM redesign for land-based power applications? Is that something you could comment on, or a little bit of color?
I'm sorry, what's the question again, please?
Let me get that again. Sorry, there's like 100 questions here. I'm trying to navigate through them. What's the maximum efficiency you think you get out of the redesign? I think is the gist of it.
We're not thinking of, we're just thinking of small gains as we go along, frankly speaking. We're just looking at every area and getting all that we can, and we'll be surprised at the end. See, what we got, but it should be, we're gaining efficiency all over the place. As a matter of fact, that part that I mentioned before, that we had all the complexity with all those complex channels within the part of the twist and turn, efficiency gains were there, just tiny bits, but efficiency gains. And that's what we're all about, just gaining every little bit everywhere that we go, component by component.
All right. There's some commercial questions here about resellers in other regions. So we actually have announced a couple resellers in Europe. One CRP, there was a release that we sent out about a week ago, and then also Excellencia as a sales agent. So if you have contacts with either one of them, you can reach out to them, and they are a representation in Europe. So if you're interested in talking to them about commercial deals. All right, let's see. Okay, this is regarding heat treatments. Like typically, what do you consider for heat treatments for a part like this? What would be involved?
Oh, this is so after printing, before we remove anything from the build plate, there's still leftover internal stresses. And the only heat treatment that we perform internally, at least at Velo, is a heat treatment just to reduce that internal stress, such that as it's removed from the build plate via wire EDM, we don't have significant deformation or movement of the part. This part in particular is aluminum, So we do a very low temperature stress relief process. I think it's around 270 C for 2 hours, and then just cooled slowly. And it's a very simple little low temperature heat treatment. You'd have higher temperature heat treatments for other alloys like titanium or especially Inconel. However, in this case, it was very simple, like 270 degrees C, kind of pizza oven temperature type heat treatment.
Okay, so just put it in right next to the pepperoni.
Yeah, yeah.
All right. Is there a lot of hands-on work to prepare a part for print?
Hands-on as far as you're working virtually. Flow is all based on the computer. It's based on CAD. It's the print preparation itself is, yeah, it's hands-on if you're hands on the mouse, but you're not really touching a tangible part until it comes out of the printer.
Yeah, I think mainly it was around getting it ready for flow and using flow to prepare. Like, do you have to do parameter development or anything like that?
No, so we don't offer an open parameter set. We qualify and provide a parameter set for the user. So that being said, there are opportunities for the designer to apply process overrides. We have an override for turning off contours. If you want to print a lot of material fast, you can turn off the contours, and that's done with a process override in Flow. And that just helps with throughput of the printer. There's also, to resolve a very small hole, we apply what we call the miniature process. So there is some work that needs to be done. Flow doesn't do everything for you, but it is very intuitive with selecting these faces and these regions in the CAD. And then once you've done all that, added any support material that you need, then you just click prepare for build, and Flow takes care of the rest.
All right. What's the powder size diameter that the print's using?
That's a typical laser powder bed fusion system distribution. I don't remember exactly what it is offhand, but it's I think the range is around 20 to 100 microns, somewhere around there.
So nothing like small sizes where they have to find different suppliers or anything?
No, we don't play any tricks with our powder size distribution. We don't stratify anything. We don't mix small particles with large particles or anything like that. We buy it, dump it in the machine, hit print.
And what materials are qualified right now for printing?
So right now we have Inconel 718, we have Hastelloy, Hastex, C22, titanium 6.4, aluminum F357, which is what this KW microgenerator was printed in. We are also working to qualify Inconel 625 right now. Then we have a few other proprietary materials for a few customers, but those are not readily available.
And if a material is not on the list, what would be the process to qualify?
So we roll that in with a machine purchase. If the customer buys a machine and we don't have a material available for them, say a copper alloy or something like that, we would roll that into the delivery of the machine, and we do that in parallel. So we have a manufacturing facility that would build a printer. Then we have a laboratory and process development facility that will develop the process in parallel with manufacturing the system. So, if we have to develop a new process for that customer, it doesn't push the lead time out by any means.
Okay. Enrique, I've got one for you. Who do you envision as the customers for this product, the microgenerator?
Everybody.
Are you selling any Batmobiles? Sorry, that's not one. I keep trying to get somebody to print a Batmobile and they just won't do it. All right, here's one about qualification. Are there any differences in qualifying an AM part versus traditional manufacturing? And I'll leave this open for anyone who wants to talk to them.
I personally, in my experience, the challenge is, metal AM is still pretty new. Casting's been around since, I don't know, thousands of years. Machining's been around, 100 years. Metal AM's been around 30, 40 years, and it's still in its infancy. So there's a lot of reluctance in, the end users or the end application to accept it as safe, acceptable, or certified. So it's a bit of an uphill battle sometime to certify a metal AM process, but that's what we're really targeting as one of our main goals through, especially the Assure qualification software, is really getting that confidence in the technology built up so that it is more readily accepted as far as something like a flight hardware component or something like that.
Here's an interesting one. Okay, so what about changing the powder to a different material?
So it's possible. I'm not going to say it's easy. In our system, there's a lot of plumbing. There's a lot of tubing, internal passages where the powder moves through. So if you're going to switch powders in a printer, we do not recommend doing that. However, it is potentially possible to do, but it's rather labor intensive. We'd recommend dedicating one printer to one material type. It's not where we can just pull a hopper out and put a different hopper in and hit print. Cross contamination would be a concern. So you need to do your diligence, clean it out, and we don't recommend doing that.
Okay. Surface roughness. What surface roughness can you expect? And I'll kind of leave this open. Obviously, the angles play a role here.
So yeah, it's really based on angles of overhang. There's other local geometric characteristics that could cause surface roughness degradation, but in general, we quantify about a 90-degree vertical wall down to a 10-degree overhang. And we see surface roughness, and we measure it in SA of about 4 micron SA at a vertical wall, and then down to about a 10-degree overhanging feature. We see about 14 to 15 micron SA in general.
This is an interesting one. Have we looked at the possibility of machining parts while they're still attached to the build plate in order to get kind of datum alignment?
No, that's something that, there are machines out there that do that. I've seen some that will machine away material with, it's kind of like it's not laser powder bed fusion. It's a different process so that, you're a little bit more open. You can have cutting fluid in the chamber. If we tried to do machining and cutting, especially with fluid, we would create a mess in our process. So no, machining needs to happen outside of our machine.
How many lasers does this printer have?
Currently, the Sapphire systems that are available today have 2. The Sapphire XC next year will have 8.
Got it. Well, I think we're actually doing really well here. And yeah. So any closing thoughts? And I do want to say, please list any way that the people can get in touch. There were a number of questions on how do we reach out? How do we contact the speakers? So whatever works for you, closing thoughts and ways that they can contact you afterwards. And Enrique, if you can kick us off.
They can find me at enriquez@kwmicro.com.
All right. Any closing thoughts?
Well, I'm really, I'm full of excitement, and in honesty, I'm ready to go on to the next task. I got some work for Ryan and Gene. So, and we keep talking about it. I'm just as happy as a 3-year-old running around in Christmas.
All right. Ryan, closing thoughts and ways to contact you.
Yeah. So closing thoughts. I like to leave all of these with just saying, don't get stuck in your old ways of designing. Sometimes a simple solution like in this scenario it can be an ideal one, right? And then if you're looking for performance gains, be bold in that design and seek out all possibilities for manufacturing and design. And you can reach me, or probably the best way to reach our team is just sales@nTopology.com. And then I believe my email's on the presentation deck. So take care.
All right, Gene, that leaves you.
Well, I think, my biggest takeaway from this whole process was my last job and my last role was foundry engineering, and my job was pretty much to make design engineers cry. They would have this really cool design to do a lot of really cool stuff. They'd come down to me in the foundry and they would say, no, you can't do it. You got to change that. You got to change that. You got to change that. Try again. And now working for Velo3D, I'm in a unique opportunity to not make Enrique cry, to not make Ryan cry, to say, yes, that's no problem. Let's put it in the printer and go. And, that's something that I'm really passionate about, especially with working with Velo3D. It really embraces our ability to innovate and solve problems without the compromise. So if you'd like, I'm on LinkedIn, or you can email me at gene@velo3d.com. I won't make you cry.
All right, no crying today. And if you want to contact us at Velo, just about anything in general, info@velo3d.com works as well. We have a number of people monitoring that on a daily basis, so it's not a dead email. We will see it, and we will be happy to get back to you. And I think we're all up on time. Thank you, everybody, today. Great session, and thank you, everyone, for attending. Lots of awesome questions. And we'll let you get back to your Wednesday, and hopefully have a great rest of the week. Thank you very much.